1 TeV. Now you see that one can reduce F to down to 1 TeV, one can produce the Higgs boson mass, which is consistent with no custodial SU2 breaking and X on the exotic quark mass about 900 GeV. Now, how about the other heavier scalar mass? One can also estimate their mass. It turns out one time there are two additional CP even scalars. Their mass are basically predicted to be heavier than the corresponding fermion mass, heavy fermion top partner mass. So since the scalar is always more difficult to be found than the fermions, so one would expect that if you find this thing to test this model, the first thing you will see are these fermions in top partners. Now let me conclude. So here we see that light Higgs boson can arise naturally in a composite Higgs model, where the top and the new vector-like quark participate in strong dynamics which preserve a larger global symmetry. And through spontaneous breaking of this large global symmetry, you can produce a pseudo-non-boson Higgs compatible with 126 GeV Higgs discovered at LHC. Now, without the custodial symmetry breaking, in fact, the constraint from the weak isospin violation is very strong, which push everything to be very heavy, so that they are all out of reach of the LHC. But one can at least test this T parameter at the future E plus E minus collider. On the other hand, if you are willing to make the model more complicated, you extend the model with a custodial SU2 symmetry, then you can reduce the fine tuning and make all the spectrum much lighter. The top partner can be lighter than 1 TeV, which will be tested at the 14 TeV LHC. I think 14 TeV LHC can test their mass up to probably 1.4 TeV or so. Most of the heavy states still require high energy machine beyond the LHC, though. Okay, I think that's all I want to say. Thanks for your time.
Questions? So for the top quark condensate, do you need to introduce new gauge fields in the underlying theory?
Here we didn't discuss what the underlying theory is. Of course, we don't know many options. Right. Obviously, gauge symmetry would be a very natural choice, like the top color type model.
So I'm surprised that you didn't start right from the beginning, requiring an SO4 symmetry as you do, of course, as you do breaking, as you do. But let's say, since I'm an experimentalist, you only talked about the T oblique parameter, and I thought that when you have these scalar loops, both the S and T parameters are modified. If I forget about this, effect, I think the T actually gets a negative contribution if you have scalar.
These scalar loop contributions are very small. We calculated, yes, compared with this. Although to the S parameter, it's very small.
Why is that?
First of all, we only introduce vector-like fermions, which basically, to a first approximation, doesn't really contribute to S at the lowest order. And second, because of the constraint of T parameter, it already pushed the whole spectrum up. It's already close to the decoupling limit. That also makes the scale
because
small.
you mean the coupling is really small to the scalars.
No, the coupling is not small, but the spectrum is quite heavy. So
Other questions?
So the way we start, because we just start from the simplest model, it's always a
So it's
trade-off between
It's historical.
simplicity and the tuning, right? It's also true for supersymmetry too, right?
Yeah.
If you want the, either you choose for MSSM, you have to tune the Higgs map, or you add additional contribution to make the Higgs heavier, then you need more complicated model. It seems
You didn't say anything about the row. I mean, your model doesn't predict these rows if they exist. This vector.
well, yes.
I mean, there's not a good observable for.
It could be, but it's not much of a prediction in this model. It's sort of like a parameter. We don't really have a control on how big it is. We can only say it cannot be too heavy. So in fact, it can be. Also, another thing, we say the cutoff, we parameter by m rho, but it won't be exactly rho mass. Usually it's just roughly rho mass. So you cannot take our m rho as literally as the rho mass. So
Any further questions? So it seems that all the strong interaction is just contained in itself, right? It's not accessible by the W boson. So it's very orthogonal to the usual way of thinking.
yeah, let me just all these in fact all these pseudo Navier-Stokes boson will predict some modification in this in Higgs to W coupling.
But you
There is
said
a suppression.
Oh, okay. So you started with say 0.2%, right? But you have this custodial symmetry. How
Right.
does that change?
Oh, this can be much bigger. It's basically V squared over 2F squared. So in this case, V can be close, be about 3%.
Okay, so that's much more probable there. So that's a further signature.
Yeah, yes,
for
yes.
this
I
custodial.
forgot to prove
Yeah,
the
okay.
thing here. So it can go up to 3% when F is down to 1 TeV.
But this provides no insight on lighter fermion mass generation.
No.
It looks like in general hard to avoid SCSC.
Yeah, that's a total different story. One need to assume underlying theory has some favor symmetry, then it will be fine.
Okay, so I see no further questions. Let's thank Professor Cheng again. Professor Cheng has been here throughout the month. He will be here until the end of this week. So if you want to have further discussions with him, try to catch him. He's up at
But not tomorrow.
Not tomorrow. Are you going to Tsinghua or NCTS?